Wow, amazing.
Okay, so today we're choose the game Subway Surfer, and we're gonna introduce you about the physics inside the game. 私は in the sea.
Amazing. What happened? But what did you say? I'm sorry. Sorry. What 私は誰ですか？
私は箱物です。
Wait, you're too fast. You're
イムです。
Im-san.
ドンジャイ。イムさん。
I cannot find Im-san.
ドンジャイ。DUANG。
Oh, okay. But this become Im-san? Okay. It's totally different, no?
We use our nickname. That one is our real name.
Fine. No problem. And then, あなたは?
Janice.
Janice, I found it. Janice. Okay. That's good. Janice, I found. And then, あなたは?
You can see our name on the slide. You put our hopes.
Park Holmes. Eh? Park Holmes-san. Okay.
Oh, but the transistor is just Bunsu. P-O-N.
Are you in this group?
Bunsu.
Punsu, right?
Yes.
Isn't Anna is easier? No?
Yes.
You're Punsu, right?
Yes.
Okay. But also Andin, right?
Yes.
Okay. Okay. Did you change your name from last year? Okay, then.
Then this Bua Shompu.
Oh, you guys' nicknames are completely different. Jan Ji. Okay. Hi. Nice to meet you.
You are in.
That I know. But I don't find. I don't know your real name.
You are in.
Okay.
Yeah.
Okay, good.
Okay. And the main character is
Oh, 私は友です。はい。
And today we have choose to presenting the game.
Oh my God.
Subway Surfer.
Oh my God. I have to take this picture. What's going on? Oh my God. Oh.
Now let's see what is Subway Surfer's game.
Okay. Oh, I know this. I'm used.
Yeah.
How do you know How do you find my picture? Oh no.
So first of all, we're going to give you the game descriptions, which we know that most of us already know how to play the games. So it all started with a teenager boy or girl have the grabby on a train, which is illegal. So the police try to catch them. So as he runs from the police, he has to run through the obstacles and collect some items. So the games will end whenever the boys or a girl have been collide into a obstacles.
Sorry, you're Parkon, right?
Yes.
Okay.
And this is your role.
No.
Yeah, it's your role.
Is there any physics related to game?
Yes.
Well, actually, that's the question I was discussing with Boy this morning. Subway, is there any physics?
So firstly, we're gonna talk about momentum.
Okay.
So, what is momentum? Momentum is a product of an object's mass and its velocity. Simply said, momentum is a force gained by motion or by a series of events. P equal mv is the equation for momentum. As either mass or velocity increases, momentum increases.
So you're Janice, right?
Yeah.
Okay.
So, firstly, we must understand that in Subway Surfer, it's a game, so it's like a closed system, isolated system. So, the law of conservation of momentum applies. The law of conservation of momentum states that in an isolated system, the total momentum of two or more bodies acting upon each other remains constant unless an external force is applied. Therefore, momentum can neither be created nor destroyed. As the equation below states, total momentum before is equal to total momentum after.
Mhm.
So what if this boy hit the train?
So the boy will get hurt, and there's some physics involving here. So we're gonna talk about collision. There are two main types of collision in this game:
Mhm.
elastic collision and inelastic collision.
Okay.
When the boy hits like a stationary object such as a wall or an obstacle, it's usually elastic collision. As kinetic energy and momentum is conserved, the boy will usually bounce back and fall down. And there's another one, inelastic collision. So when the boy gets hit by a moving train, kinetic energy is not conserved, but momentum is conserved. Therefore, the boy will actually be being thrown back by the train, following its direction towards the screen.
Okay, let's talk about their next magnet. The next topic is the magnet.
Okay.
Ooh, what's this? This one.
Okay. You're asking.
The magnet is the material or the object that produce a magnet field. This magnet field is invisible but responsible for the most notable property of a magnet. A force that pull on other former magnetic materials such as iron, steel, nickel, cobalt, and attract to repulse other magnets. As you can see this picture, there's two sides, north and south, or plus or minus. If it's opposite, it's gonna be attract each other. But if it's the same size or the same south, it's gonna be not attract to each other.
Okay. Sorry. Your Janji Imsan. Where did it go? I lost you. Okay. You're in the end. Okay. Sorry.
Okay, as you can see in the game, the magnet is attracted to the coin. It's because the material of the coin makes from like copper, balls, cobalt, or nickels. Those are material are attracted to the magnet.
Okay.
Yeah. So have you ever think why most of country use those materials to make the coin? Because the material are strong and durable in USA. Like nickel, it has some like unique electrical properties. Therefore, it's an important component to use this distinguish real coin with counterfeit coin when having to use with worthless coin over the machine.
Okay, so let's talk about common physics that we can see in this game, but we might haven't noticed it. So in this subway game, right, the developer often like wants user like player to get a realistic experience. So gravity in this game is kind of similar with the real one. So all objects, including all factors, subjects, and item, would be subject to gravity. Which means that, like for example, when all character jumps, all character gonna fall downward to the Earth's surface. So what is gravity? Gravity is a force of attraction. It's pull objects with mass toward each other. The more massive an object is, the stronger its gravity pull.
And this is Newton's law of gravitation. F is magnitude of gravitational force attack between mass 1 and mass 2, which is right here.
Mm.
And when we talk about force, there's something happen with, there's something exit to, which is friction. So friction also impact like how character interact with obstacle
Mm-hmm.
in this game. For example, if all characters slide down a subway car roof, right? The friction will exit, and the friction is like between their feet, like all character and the roof surface.
Mm.
And also, you can see here when they skateboard, the friction is exit and is kind of make them slower a little bit when we slide in subway roof.
Mm.
So now we're going to move to the next topic, but let's you guys imagine about following these. So, for example, if you are on a train station, you are waiting at your platform, you're standing still, and the train passes you.
Mm.
It's the train seem fast. And then another situation is that you were walking to your platform and the train passed you in the same direction.
Mm.
It seemed not that fast. And then another situation is you were walking to your platform, but the train passed you in a different direction. It seemed very fast. Why? So it's all related to relative velocity. So
Okay.
what is relative velocity?
Hmm.
Relative velocity is all about the reference, frame of reference. So it is the time rate of change of the relative positions of one object with respect to another object. It would be easier if we use an example.
Hmm.
So we have object A with the velocity A, and object B with the velocity of VB.
Hmm.
And we're going to find the velocity of object A related to the object B.
Hmm.
So we're going to get the VAB equal to VA minus VB. And this explains why when you were walking past the train in a different directions, it seemed faster. And this is another example, which is if the boy velocity is 5 meters per second and the train velocity is 10 meters per second, what is the velocity of the boy with respect to the train? You can get v of boy minus v of train. And the train is in the different directions, so you're going to get 15 meters per second.
Is that your picture?
Yes, sir.
Oh. Okay.
And
So I usually give everyone mini homework.
Yeah.
So what happens if the velocity of boy and train is, say, very close to the speed of the light? Maybe can you do a little bit investigation and then put it in a report?
Yes.
Just a little bit is fine.
Yeah.
Okay, good.
Okay, and the next physics that related to subway surf is aerodynamics.
That's interesting.
Yeah, but okay. What is aerodynamics? You might wonder this. So aerodynamics is the way that object can move through the air. The rules of aerodynamics can explain how the airplane is able to fly. And actually anything that moves through the air is affected all by aerodynamics.
Okay.
So from since a rocket blasting to maybe a kite flying or even the cars riding. Since they are surrounded by air, even the cars also affected by aerodynamics.
So you're Genji, right?
Genji, yeah.
Genji. Okay, good.
So there are 4 forces of flight in aerodynamics. The 4 forces of flight are lift, weight, thrust, and drag. And this force can make object move up and down or move forward or backward, faster or slower. And the amount of each force compared to its opposing force determines how an object can move through the air.
Mm.
So it's gonna explain how the plane fly. And also when you're running, you also have aerodynamics happen because you run through the air. So here, yes. When you're running,
What are you doing? Oh my God! Can you go back? Is this a video?
yes.
Oh no!
But what if you run through the tunnel?
I want to hide. Oh my God! Did I have a bad hinge? Okay, good.
Okay, so
I
let's talk about when he runs into the tunnels.
okay. Sorry, you finished?
Yeah.
Okay. So can you investigate a little bit? You talk about where you talk about flight, right? Okay. How about what happens if Earth's air density is half? Then what happens to the airplane? Can you think about it? Okay. Okay. And then
Okay, so next we're going to talk about
so
whenever
back home again.
yes.
Okay.
Let me go through the tunnels.
Channels.
Yeah, tunnels.
Okay.
So first of all, the picture on the right is where there's different infections whenever the trains are on the open air or in the tunnels or in the railway line. But today I'm going to talk more about the tunnels.
Mhm.
So whenever the train going through the tunnels, they normally going to lower down the speed. But why? These are the 5 aspects.
Oh,
So
that's
first,
interesting.
is
Yes.
safety. Of course, we know that with the reduced amount of speed, help improve the safetyness. Second is in visibility. So what is visibility? This is the way we see. Because inside with the minimum of the light inside the tunnel, it's really hard to see obstacles or stuff inside. So they have to slow down the speed. The third one is ventilation. What is ventilation? Ventilation is because whenever the train goes into the tunnels, the oxygen have been really reduced, which causes the gas. So with the minimum of oxygen and the air in between, it causes that there might be some kind of gas. So we have to lower down the speed to lower down the gas. And the fourth one is noise and vibration. So the noise and vibration is also talk about the pressure wave, because with the noise and vibration, it reduce the amount of airflow, which it improves the pressure wave, and the passenger might have some kind of heard of a noise, or even they might get some like hardness on their ears or feel uncomfortable. And the third one is aerodynamics. So I'm going to talk more about the aerodynamics part.
Okay.
So Janji have already taught about the open air, but I'm going to talk more about the tunnels, which aerodynamics are different in the air and in the tunnels. So with the aerodynamics and the tunnels, whenever the train has entered or exit the tunnels, they have to reduce the speed to reduce the aerodynamic force, because aerodynamic force have much more potential, have much more effect of aerodynamics inside the tunnel more than the open air.
Okay.
And with the slow down the train, it makes a stable and potential stable more because of the change of the airflow. And I'm going to talk more about the aerodynamic drag and one of the effects that cause in the tunnels. So what is the aspect of the aerodynamic drag? It is a combination between a friction drag and pressure drag. And in the aerodynamic drag, whenever the train enter or exit the tunnels, there will be more of the fluctuation in the aerodynamics. And it will cause the pressure wave to increases. And also, whenever the pressure wave increase, it is because of the air. Because whenever the train goes into the tunnels, there's much more smaller space in between, which cause a squeeze of the air, and it will turn into a shock wave, and it might cause a discomfort in passenger.
So the pressure wave, pressure is for the pressure drag. It's from the front of the train.
is also related to like the model of the train. Like
Okay.
also because when entering, it's like with the modeling of the train, it will cause different effects.
Okay. So what is the y-axis here? CD?
CD.
Yeah.
It's like like this one is a aerodynamic drag with respect into the pressure wave. Like when it's going, it's like inclined.
Okay.
Yeah.
Can you check how much pressure is going to increase when train with certain speed goes into the tunnel?
Sorry.
I want to know how much the pressure is going to increase when a train goes to tunnel. Well, it depends the size.
It depends on the length of the tunnels.
Mhm.
It depends on the size of the train and the motion. I mean
Speed, right?
the speed and also the
Shape.
model.
Yeah,
Model.
shape of the.
Yeah. So it all depends on how the tunnels are created.
Okay.
Yeah.
Can you check one example? Show one example in the report.
Oh, what's the in the report?
One example.
Oh,
No, not now.
yeah.
In the report. Is
I
that?
already sent the report.
Yes. You just add it and then we
I'll
send
send it again.
Yeah.
Okay, sure.
Sorry, so everyone have to add it or just?
Yes, that's what I'm trying to do.
Okay, sure.
Did I give you a homework? No. Okay. Maybe I'll think about something later. So when we go into the tunnel in a train, we feel like the ear is, so the pressure must be increasing, right?
Yes.
So
And it's
so
because of the pressure.
right. So I want to know, how much it's increasing. Maybe it's useful to know.
Yeah, I can.
Thank you very much.
Okay, so this is like the aerodynamic drag of the tunnels, like the train tunnels equations.
Oh, good. Very nice.
So the F is an aerodynamic drag. The C is a time the train have gone through the tunnels, respectively. The P is the air pressure. The S is the area of the train. And,
Okay.
And then the VTR is the speed.
Okay. So C is what?
C is the time.
I'm CX is what? Is it time?
CX. It's a time respect for the train. Like, yeah, it's a time. Like the time when it passed through the tunnels. Like the time. The time that.
How long?
Like going to the tunnel 1 second, 2 seconds, 3 seconds like this? Is C?
Yeah, the C.
Are you sure? Because usually time people use T, no?
It's like respect to it. Like,
So that doesn't make sense because if it's time, it's 1 second, 2 seconds, 3 seconds, it's proportionally increase the drag, right?
it's a time function.
Oh, it's a function. It's
Yeah,
not just
It's
time.
more like a function. But it's like related to the time.
I'm not sure about it. It's X means the function of position, no? If it's a function of time, it would be T.
I'm not sure, but from what I researched, it said it's like a function of the time passing through the tunnels.
Okay. Well, it's the same thing. If the train speed is the same, the time and speed scale is the same, right? Right. I mean, sorry, time and position scale is the same. And then rho is the air density, and then S is what?
The S.
Is area train.
The S is the area of the train.
Okay. So the velocity is okay. So the velocity is area. Okay, density. Where's the size of the tunnel? It doesn't matter because I can imagine, as you said, if the tunnel is smaller, then probably it's more difficult for a train to go through. Right? If tunnel is very big, then it's okay, right? Like if we go to Iran, then the tunnel is very small and the traffic jam, right?
Yeah.
So I thought there might be the size of the tunnel maybe in here too.
Sure about it.
And then this C is a function, so it's not. So, but then in the previous one, can you show the graph? The previous one. So this actually, after a certain time, it decreases, right? So maybe when first suddenly increases when the train goes into a tunnel, and after a while, it just go to equilibrium, and then it's the train get used to the environment of the tunnel. So this decrease, where can we see in the equation? Oh, okay. Sorry, I didn't notice. I usually ask students to turn on because you guys speak here, right? But then I forgot to ask you. So sorry. But I mean, you can tell me earlier, no? Why he's telling me at the end of the presentation. But anyway, it's turned on, so it's okay. And then thank you very much for group 10. It was a great presentation. So thank you very much. Okay, then we have 5 minutes break and then we continue the regular lecture. Okay. It's still recording. And then could you face the camera when student is speaking and face the camera to the speak? Oh, if you were just shooting that. And this probably is better there because it's not covering the whole. Okay.
มันมีคนมาดูประสบการณ์ มันเป็นเขินแบบนี้ค่ะอันนี้มีสิทธิ์เขิน
Okay, shall we get started? And then when we try to start, somehow. Okay, so this is actually a very important part. We're starting from continuing from the last week. So this is electronic safety. That is very I think important for everyone. So one thing to note is 100 milliampere. This is a dangerous level. So if 100 milliamperes current goes through your body, you die. I mean, basically your heart stops. This is actually very small amount of current. For example, your laptop, you guys have laptop, right? Oh, you don't. You have iPad. Okay. So your laptop, do you know how many amperes? Say, okay, I have a laptop because I'm richer than you. So how many amperes of current going through this? Do you know? You know? True. This Taiwan is 100. Is it 100 or 110? 110, right? And this, for example, this is a laptop. It's something like, I don't know. But anyway, this is like several to 10 ampere. So 10 ampere, it's actually already, people die. So if I'm here connecting here on a laptop, and this current goes through me, then I will die. So this is actually human. It's going to die very, with a small current. And then what's important is that you see this kind of, is it okay to plug this out? Or maybe not. Okay, mine, I can. So if you look at the laptop, here's the third one, right? Do you know what this is for? Yes, ground. So do you use this usually? Okay, you guys are good. But honestly, I do this. I'm not using, right? It's maybe okay for a computer because, the current in the computer is not so large. Here it's large, but inside the computer it's not so large. But it's important for the high voltage ones. For example, microwave. You use microwave, right? In do you know if you're using the ground? Usually the another green cable is coming out from microwave. I recommend to use that, and also like washing machine or AC. AC is high voltage, right? Sometimes 200 volts, right? And also washing machine. There's a green ground line. I suggest double check if you're using or not. The reason for that is here. Okay. So if something broke in your equipment, and then if the current is leaked in this device, say if device, whatever it is, let's say this is your washing machine or microwave, and then it's broken inside, the cable is touching the machine, and then this is full of charges. Okay, that can happen, right? Say if something broke in your washing machine, and then if you don't have grounding, then you touch it. Say this is microwave. This computer is broken, and then it's inside. There's a full recharge, and then if I touch it without grounding, then the current is going to go through me, right? Then if that current is over 100 milliampere, then you die. So that's the danger. However, if there's a ground here, if there's this third line, this one, then if something is broken and then charge is gonna leak into the device, that extra charge is gonna go through here, right, to the ground. And then even when you touch, your resistance is much larger than the cable's resistance. So the current is gonna go through here rather than your body. So you'll be safe. And this can happen for washing machine because it's wet. Right, when it's wet. When it's wet, then something connects, then it can be charged, right? So maybe I recommend you to double check if you're using that. So that's very important thing to learn other than physics. Okay. Oh, what's going on? Okay, this is another thing. Another example of using this electricity application is this taser gun. Have you seen this taser gun? Yes. What did you do something bad?
No.
Then police show you.
My friends study about.
Your parents did bad thing?
My friends study in police.
Oh, really? Oh, okay. So you're familiar. Okay. But this is I think this is much better than real gun. So this, when you shoot, also, I don't know if in Taiwan police officers, they have this. In America, a lot of police officers, they have this. Or in your country too?
Maybe for the girl who wants to protect herself from like dangerous things.
Oh, so you can have one. And
Can we have it?
We don't have a gun, but we have the one at home.
okay, small one. Okay.
Is it the same?
It's a little different because this you can shoot, Then small cable, two cables gonna hit the bad guy, and then shocks. So it's really like a gun. And if you shoot, so say this is a bad person and try to run away from police officer, and then police officer is going to shoot, and then there will be a current, but then not large enough to stop their muscle, the bad guy's his muscle, but not large enough to kill him. So it sounds, I think, in a few slides back, it's probably somewhere around there. Here, okay. So this is this, right? So here, muscle control loss. So maybe something like less than 100 milliampere. Then that kind of current, the muscle control is going to be lost. So this bad guy cannot move his muscle. So he cannot run away or he cannot do anything dangerous. Well, the good thing is this is not going to kill that guy. But if it's a real gun, then this guy might die, right? If he hits the head or brain, then he's die, right? But this is just shocks him and then he makes him to stop. That's also. Yes?
But if that person is like not healthy. Like,
That we should consider. That's true. So maybe we should ask that guy, are you healthy or not? Are you healthy? Okay, I should. That's more polite way, I think. Yeah. Good, good. Then that's a good point. Okay, maybe I can show you the movie. The movie? Yes. So that I think. Because sometimes police officers shoot and kill bad guy, right? Of course, this bad guy did a bad thing, so maybe he deserved it. But killing is a little bit sometimes too much. Right? Do I have a sound? Or something like this. And the important thing is he doesn't die. Something like this. Okay. Okay, so that's the most important thing from last week. And then today we're going to talk about a new thing, new chapter that was remaining from last week. Today we're going to talk about this. Okay, so today we're going to talk about basically resistance. So we continue to talk about electronic circuits, and then we use these kind of symbols to describe, say this kind of circuit. We use these symbols to describe, for example, the battery. It's going to be this sign, this kind of sign. So electromotive force or EMF. And resistance is something like this. What is it? Resistance. Resistor is here. Capacitor is something like this. Maybe you're already familiar with this. So we use this kind of symbol to describe the circuit. And then today, in particular, we're going to look at the resistors. Resistor, something like this here. Say, then here, maybe you already know how you connect a resistor. Say there are two resistors, and then if they are connected in a series directly, it's very simple. The total resistor is going to be just addition of these two. Because the current is the same, so the battery, the voltage of the battery is going to be, because of the Ohm's law, it's IR1 plus IR2, because this voltage is going to be equal of the sum of these two. And then from here, we can figure out if you divide by I, the both sides, then this R1 plus R2 is going to be total resistance of the circuit. So in reality, in general, if it's directly connected in series, you can just add 1 to 3. So that's simple. And another example is what if they are parallel? They are parallel if they are connected like this, parallel, connected here and here. Then the conclusion is it's going to be like this. So 1 over R is going to be addition of 1 over R now, 3. Because in this case, the current through here and through here, if you add I1 and I2, that's going to go through the battery. So those currents, this one from Ohm's law, I1 point at 1, I2 point at 1, and then here the voltage of I1 I2 is the same because it's the parallel, right? So this point and at this point, electronic potential is the same because it's connected. So E epsilon here is the same here. Then this total current that's going through here is I1 plus I2, so it's going to be like this. And if you divide it to make it R, the total R, which is E divided I, is going to be like this, right? So that means the same as this. So in parallel, you just add in inverse. Okay. Then now, this is gonna watch how in a test, which we don't have in this class, so that's good. So what happens if you connect these parallels in this series, and then you in this, if we have an example like this, we just look at part by part, one by one. And then we first look at the parallel part. So here, this 2 ohm resistor, the 4 ohm resistor is in parallel, right? So you just combine, which one are you going to use? So if we want to calculate 2 and 4's combined resistance, which one are we going to use? Second one, yes, very nice. So you use second one, and then if you combine 2, 4, put it in, it's going to be 1.3. And then now if it's 1.33, then in a series, so if we use this one, how much is the total resistance? Yes. Did you calculate that?
No.
Yes, you found it good. So that's what happens if we have that kind of thing. Then another example is what if we have 2 batteries? I mean, actually, if you have 2 circuits, something like this and something like that, then we need to use this Kirchhoff's law, which states that the sum of voltage drops around any circuit group is 0. So this makes sense, right? In any circuit, say it's this circuit, the sum of the voltage, if you add a voltage up and down, it's going to come to 0. That makes sense, right? Because if you come back to the same place, if the voltage will be 0. And that's true for any circuit, this one or that one or this one. And then you use this, okay, this is equivalent to conservation of energy, because if you go around and then if your voltage is increased or decreased, you are gaining or losing energy without doing anything, right? So that doesn't make sense. So it always come back to the 0. Okay, then use something like this. Then we can use the equation something like this. So node A, where's node A? Okay. It's not written here. And then, okay, here. If you look at here, this point, the I1 is the current going through, is of course the addition of I2 and I3. Because I2 and I3 goes this way, and then becomes I1. So I2 plus I3 is I1. Okay. And then if you look at the loop 1, what is it? Loop 1, so the battery is 6 volt, right? So 6 volt, and then this R1 is 2 ohm, so minus 2 I1 is the current here, this is 2. And then another resistance, R3, I3 is going through here, and R3 is 1, actually, so 1. And then if you go, because you went through circuit, then it's going to be total of 0. And then loop 2, in this loop, 9 is a battery, okay, the battery is 9 volt. And then this is 4 ohm, so this is 4 times R2, I2. And this is again 1 ohm, so minus 1 and I3, and this is 1 loop, so it's going to be 0. So these two are, that's Kirchhoff's law. Okay. Then this is easy. How do you measure the voltage? In experiments, we use voltmeter, something like this. You connect this because you want to measure the voltage here and here. You connect it in parallel, and then you measure this. Because the voltmeter, this resistance is so high or much higher than this, very little current goes through here, and then most of the current goes here. So it's almost the same as this is not connected because not many current go here. Okay. The voltmeter, have you seen voltmeter like this? Maybe, I don't know, physics experiment class? Then, okay, how to measure the current is ampere meter, which is also very similar, but then this A sign is for the ampere meter. Then, in this case, you want to measure the current, so you put it in a series here, like in between. And then this resistance of ampere meter is very little, almost zero. So there's no resistance, there's no voltage here, and it just current goes through, right? It's a wire. Then it measures the current. So that's how we do this in experiment. Okay. And now it becomes interesting. So now we put capacitors in circuit. Then it becomes interesting because capacitors charge cannot be charged instantaneously. Say you have a capacitor, and then when we connect the circuit, the charges increase gradually. It cannot be like one instant, it goes something. So now the circuit becomes have time-dependent behavior. Oh, now interesting, no? And then the voltage, okay. So then becomes interesting. And now we look at the RC circuit. So RC circuit means we have resistor and capacitor, and then voltage and switch. And then when you close this switch, the current starts to running over, right? But then, and then ground at the beginning, the current is going to go through, right? Because there's nothing in it, no charge in the capacitor, so this battery is going to try to charge the capacitor. And then when the charge is for the capacitor, the current stops. Because this is actually not connected, right? So if the charge is full, there's no more current going to go through. So at the beginning, there's a current, but at some point, when the capacitor gets full, it's going to stop. So the circuit is going to be time dependent. Okay, let's look at that behavior. Okay, so let's look at the Kirchhoff-Root equation. So the voltage around the circuit is going to be zero, right? So here, the battery and resistance and then capacitor. This total should be zero. Okay, and then you take a time derivative, differentiate by time. So this is constant, and the current is going to change time, and the charge is going to change as a function of time, so it becomes zero. So this is derivative. And then you put the current is how much charge will change as a function of time. So we know this relation. So dq dt. So here you put dq dt is actually the current. So we put this I here. Then what happens is I here, and if you divide by R, it's divided by RC. And this is differential equation. And then so if you solve this equation, it's going to be like this. So current is going to be exponential function of time, which is written here. So the current is going to be decrease. As the charge is going to be stored in the capacitor, the current is going to decrease. And then the voltage of the capacitor, okay, maybe I can do that. The voltage of the capacitor, E, is E minus IR because of the Kirchhoff's law. And then I is exponential function, right? So 1 minus E minus T. So that means at the beginning, the voltage is going to increase. because this term minus term is going to be smaller, smaller, smaller until the capacitor's voltage is going to be. So that's more interesting, right, than just having a resistance or instantaneous circuit. Oh, okay, it's time to stop, so we can go more complicated circuits next week. So it'll be more and more interesting. Okay, let's stop here. Any questions?
No.
Okay, if no question, thank you very much again for good presentation. And we don't have a lecture Tuesday next week, so we continue Friday next week. Okay, let's stop. Thank you very much. See you next time. Have a good weekend.
Resistor